Many of the most important simulations in science and engineering rely on meshes. A mesh is simply a way of breaking a complex physical object or space into many small pieces. Each piece contains local information about the system. For example, in fluid simulation, a mesh might represent small regions of air or water. In cloth simulation, the mesh represents points connected by triangles in the fabric. In structural mechanics, the mesh represents small pieces of a deforming object. These meshes allow classical solvers to approximate the partial differential equations governing physics. But traditional simulators are often extremely slow. High-resolution simulations can take hours or even days to compute. So the question becomes, can we train a neural network to learn how the physics evolves directly from data? That is the core idea behind MeshGraphNets. So a mesh naturally looks like a graph. Nodes represent points in the mesh and edges represent connections between neighboring points. For example, imagine a cloth simulation. Each node is a point on the cloth and edges connect neighboring points in the fabric. If one point moves, it influences nearby points through these edges. This structure fits perfectly with graph neural networks or GNNs. At time step t, every node contains information about the system. Examples include position of a cloth vertex, velocity of a fluid particle, pressure or density in a flow fluid. The model first encodes these values into feature vectors. Importantly, it does not rely on absolute coordinates. Instead, it uses relative positions between neighboring nodes. Why? Because physics depends mostly on local interactions. For instance, a cloth point moves because of forces from nearby cloth points. A fluid cell changes because of neighboring fluid flow. So the model learns these local physical relationships. So once the graph is built, the network performs message passing. Each node sends messages to its neighbors, as you can see here. These messages represent how one part of the system influences another. Think about a flag in the wind. In the wind, if the wind pushes one corner of the cloth upward, nearby nodes feel the tension and move too. Through several rounds of message passing, the network learns patterns like tension propagation in cloth, pressure propagation in fluids, deformation in elastic materials. This is essentially the neural network learning the local rules of physics. After message passing, the network predicts how the system changes. For each node, it might predict things like acceleration, velocity change, pressure change. These predicted derivatives are then integrated to produce the next simulation stage, as you can see here. So the model learns a function state t to state t plus 1. Once trained, we can repeatedly apply this prediction to simulate the entire trajectory.